Assalamualaikum everyone. Today's episode is a brief revisit of the quantum states of the hydrogen atom. How many distinct states of the hydrogen atom with the principal quantum number 4 are there? Find it out, watch, and learn. The given question is how many distinct states, that is N, L, and F sub L, of the hydrogen atom with N equals 4 are there? And what are their energies? Before we answer the question, let's first look at this table. Alright, this is a table showing the quantum states of the hydrogen atom. For the first three energy levels or principal quantum numbers 1, 2, and 3, we have their corresponding number of energy sublevels, or also known as the orbital quantum number, denoted by small letter L. And in the third column, we have the number of what we call magnetic quantum number, denoted by small letter m sub L. And in the fourth column, we have added the what they call spectroscopic notation, 1s2, s2p, 3s, 3p, 3d. All right, this is how they label the orbitals, okay, at the different energy levels in chemistry. And in the last column, we also have the energy levels expressed in terms of the capital letters K, L, and M, corresponding to the principal quantum number n equals 1, n equals 2, and n equals 3 respectively. So they call this the shells. K, L, and M shells. All right? The energy sublevel, which is also called the orbital quantum number, denoted by small letter l, can be determined, all right, by using this formula. All right, so L ranges from 0 to n minus 1. For example, if n equals 1, right, that gives us the value for L. N equals 1, that means L is could only be 0. All right. If n equals 2, so that means 2 minus 1, we have 1, plus the first possibility, which is 0, so we get 2 possible number of orbital quantum number, 0 and 1. If n equals 3, that means 3 minus 1, that gives us 2, all right, plus the first one, which is 0, so that gives us 3 possible number of orbital, all right, or orbital quantum number. Okay, L could be 0, 1, or 2. In the case of the magnetic quantum number m sub L, also known in chemistry as the electron orbitals, all right, we can get it using the formula ml equals twice the number of uh, orbital quantum number L plus 1. So for example, if n equals 1, all right, and L equals 0, then the only value for m sub L is 0, all right? If n is 2 and L is 0, all right, m sub L can only be 0. If n is 2 and L is 1, okay, ml or m sub L can be either negative 1, 0, or positive 1. If n equals 3, but L is equal to 0, then ml can only be 0. If n equals 3 and L equals 1, okay, ml could either be negative 1, 0, or positive 1. And if n is 3, but L equals 2, then ml could either be negative 2, negative 1, 0, 1, or 2. So in terms of spectroscopic notation, this magnetic quantum number negative 2, negative 1, 0, 1, and 2 can also be described in terms of spectroscopic notations as 3dx, 3dy, 3dz, 3dxy, and 3dxz. For the given problem, we emphasize that n equals 4, okay, if you noticed earlier, n equals 4 is not included, okay, in that table. So that is what we're going to discuss. All right. We are looking for the total number of distinct states of hydrogen atom, and we'll do this by first finding the orbital quantum number and the magnetic quantum number. All right. So we already explained earlier how we determine the number of states for the orbital quantum number L. It ranges from 0 to n minus 1. Right? And for the magnetic quantum number m sub L, all right, the number of states is just equal to twice the number of the orbital quantum number L plus 1. And the other target variable, this problem, is to find the energy at the given principal number n equals 4. Okay? And we will be using this formula. The amount of energy at any higher principal number or principal quantum number, small n, all right, is just equal to a constant negative 13.6 electron volts per n squared. All right. This constant negative 13.6 electron volts pertains to the energy of uh, what we call the ground state. So in the ground state, the energy level has been determined to be equal to negative 13.6 electron volts. Moving on to our computations. First, determining the number of orbital quantum number, small letter L, all right? Or we refer this as the number of energy sublevels, and it ranges from 0 to n minus 1, all right? Or the number of sublevels is also equal to the number of main energy levels, all right? So when L equals 4, substituting in this formula, so that would be 4 minus 1, and that gives us 3, plus the first, all right, the first sublevel, that is 0, that gives us the number of sublevels equals 4. And these are L could be 0, or L could be 1, 2, or 3. All right? Now, for the magnetic quantum number, m sub L, all right, using the formula 2L plus 1. So 2L plus 1 gives us the number of magnetic, or refers to the magnetic quantum number. In chemistry, that's also called the number of electron orbitals, right? So, if the number of sublevel, energy sublevel is 0, that's L equals 0, substituting here in the formula, okay, the number of electron orbitals, or magnetic quantum number, would be 2 times 0 plus 1, all right? That means we will only have one electron orbital, all right? In short, m sub L can be only 0. So that means at this early, we have one state, distinct state. Continuing with our calculation, when L is equal to 1, all right, m sub L can be negative 1, 0, or 1. Let's check. Okay, L equals 1, so that gives us 2 times 1, that's 2, plus 1, that's 3. All right? So the number of electron orbitals, all right, would be 3. That means ML can be negative 1, 0, or 1, for a total of 3 states. All right? Next, if L is equal to 2, so L is equal to 2, M sub L can be negative 2, negative 1, 0, 1, or 2. All all right, for a total of 5 states. How we get 5? Let's check. So with L equals 2, that means 2 times 2 plus 1, that gives us 5. 5 electron orbitals, or the number of states equals 5. Okay? Either ML could be negative 2 or negative 1 or 0 or 1 or positive 2. Lastly, if L equals 3, then how many states there will be? We say if L is 3, that would mean 2 times 3, 6 plus 1, we will have 7. Alright? So there will be 7, what we call electron orbitals, or there will be 7 distinct states. And these are ML could be negative 3, negative 2, negative 1, 0, 1, 2, or 3. Hence, the total number of distinct states is 1 plus 3 plus 5 plus 7. That gives us 16. So there are 16 distinct states. Alright? In chemistry, they usually call this electron orbitals. Alright? And according to Pauli's exclusion principle, okay, there are only two maximum number of electrons that can occupy a single orbital. So with 16 distinct orbitals, all right, there will be what we call 32 electrons occupying this 16 orbitals. And finally, or before we proceed to the calculation of the energy, all right, corresponding to the excited state n equals 4, all right, we just refer you to the way the 16 orbitals that we obtain, how it is represented, especially in chemistry. All right. So we are referring to the fourth energy level or quantum number n equals 4. All right. So the distinct orbitals or states can be labeled as 4s, 4px, 4py, 4pz. All right. In short, there are three orbitals um, or p orbitals. They are distinguished as px, py, and pz. Now, for the d orbitals, there are five, such as 4dx, 4dy, 4dz, 4dxy, and 4dxz. And for the f orbital, all right, still in the fourth energy level, there are actually 7, such as 4fx, 4fy, 4fz, 4xy, 4fxz, 4fyx, and 4fyz. Alright? So if you add all of this number of orbitals or states, there will be 16 all in all. Alright? 1 plus 3, so that's 4, plus 5, that's 9, and plus 7, for a total of 16 distinct states or electron orbitals. So moving on to our last question. Okay, finding the energy at n equals 4. Okay, using the formula negative 13.6 electron volts divided by n squared, where our value for n is equal to 4. So substituting, we'll get negative 13.6 electron volts divided by 4 squared, and doing our math, we will get the amount of energy at the fourth energy level, or n equals 4, equals negative 0.85 electron volts. Evaluating our preceding answers, we say that for a given number of n, the total number of states, all right, for the quantum numbers n, l, and m's of l, okay, turns out to be n squared. Okay. In this problem, where n equals 4, so there are 4 squared or 16 states. The ground level of hydrogen atom has n equals 1, and the energy at the ground level is equal to negative 13.6 electron volts. All right? The n equals 4 excited states have a higher higher energy, okay, less negative, in fact, but higher amount of energy. And we also add that stationary states with the same principal quantum number have the same energy, even though they have different values of the orbital quantum number L and the orbital magnetic quantum number m sub L. Okay, the same amount of energy, all right, for a particular principal quantum number. So that completes our tutorial for today. Till the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.